Hi everyone, and welcome to Natural Resources Canada's e-training module on operations, maintenance and commissioning. This course has been adapted from the U.S. Department of Energy's Federal Energy Management Program training material on implementing deep retrofits. This training is being delivered through the Natural Resources Canada Greening Government Services to help federal departments and agencies plan and implement projects that reduce the energy use and greenhouse gas emissions in their buildings, laboratories, other facilities, and vehicle fleets. Over the years, Natural Resources Canada has been successfully developing comprehensive methodologies, practices, and tools to reduce energy consumption and greenhouse gas emissions for the private and public sectors, including the federal government. Since 1991, NRCan has provided enhanced technical support to Government of Canada organizations seeking ambitious greenhouse gas emission reduction actions from their building and fleet operations. This training will support federal organizations to meet their commitments and lead by example. Federal facilities have committed to reducing emissions from their operations by 40% below 2005 levels by 2030 and by 80% by 2050, as outlined in the 2016-19 Federal Sustainable Development Strategy. This initiative also supports the commitment by Canada's federal, provincial, and territorial First Ministers to scale up efforts to transition to highly efficient buildings and zero-emission vehicle fleets, as specified in the Pan-Canadian Framework on Clean Growth and Climate Change. I'd like to start by covering our objectives for today. Upon completion of this seminar, you will be able to give an up-to-date definition of operations and maintenance, explain the relationship of O&M on commissioning, discuss the benefits of a well-run O&M program, explain some of the common barriers to O&M and how to overcome those barriers, list 5 performance measures for an effective O&M program, explain the term OMETA in terms of a complete O&M program, explain life cycle implications in O&M from new component design to replacement, discuss the benefits of each of these types of maintenance: reactive, preventive, predictive, and reliability-centered. And locate the resources to support you as you develop your O&M programs. This course is broken into the following segments. The first question you need to ask is this: is operations and maintenance part of your commissioning process? If not, you need to incorporate it. In the next few slides, I'll explain why. First, what is commissioning? Commissioning is the process of verifying that the components of the systems within our facilities operate as they should in accordance with design expectations. It's also important to understand the difference between commissioning, retro-commissioning, and recommissioning. Commissioning is the quality assurance process that begins during the design of a new building and continues through construction, occupancy, and operation. If a building was not commissioned originally, retro-commissioning can occur later. Finally, recommissioning is a re-optimization process for buildings that have already been commissioned. It is done to ensure that building equipment and systems are operating optimally to meet current occupant needs. If they do operate according to design, how long are they going to operate that way? Well, without proper O&M, it's been shown that the answer is not very long. A well-designed O&M program is critical to commissioning. It's critical to maintain system performance, to extend the equipment and component operational life, and for cost avoidance. Both the cost avoidance from an energy standpoint, which obviously is key, but also cost avoidance from having to replace the components and material at your facilities. So what is O&M? What do they mean by O&M? Here's a classic definition of what many people think O&M is. Basically, just routine maintenance and fixing things when they break. Today, we'd like to propose a modern definition of O&M, a view that operations and maintenance is not just operations and not just maintenance, but really inclusive of 5 key areas: operations, maintenance, engineering, training, and administration. All of these are key to a successful O&M program. We'll talk about how these fit together a little later, and how we can evaluate each of these areas to determine whether or not they're contributing as they should to the O&M program. Many surveys on O&M have been performed throughout the years, and the findings show there are several O&M issues that are commonly seen. These issues include operating equipment in manual override and incorrectly adjusting equipment, There are also frequent leaks in various systems, faulty control systems, and problems with HVAC equipment. None of these issues are unusual, and I'm sure that many of you have encountered one or more of these problems at your facilities. These problem areas offer a great opportunity for energy savings. In fact, one U.S.-based survey indicated that energy savings of 5 to 20% are common and that most of the fixes are low cost or no cost. There are some simple O&M type repairs that can turn around and save some major dollars. Through this course, we'd like to promote an O&M first philosophy. Often at our facilities, O&M is not put first but last. Frequently, the first place that management looks to cut costs is in the O&M budgets. But that's not the way to solve problems, save energy, or to save money in the long term. The benefit of putting O&M first is reducing energy consumption, as well as reducing unscheduled equipment repairs or replacements. We'll discuss that more later when we discuss reactive, preventive, and predictive maintenance. If we place O&M first, we increase the reliability of our facilities. We'll also reduce capital cost because if things aren't breaking, we don't have to replace them. We're going to try to get the design life out of the equipment that we put in a facility and ensure that other energy conservation technologies achieve their expected cost savings. We validate and verify that the new equipment that we put in and our measures actually save and conserve energy. And if things aren't breaking all the time, not only is safety going to be improved, but also operations and maintenance staff morale. So what are the barriers to putting O&M first? Well, we touched on a couple of the biggest barriers already, starting with the budget. The budget is obviously a big barrier and one that's hard to overcome. Management may not want to pay for O&M because they might not understand the importance of it. It's important to educate management on the benefits of putting O&M first. There could also be limited staff and a lack of training. Inadequate diagnostic equipment can also exist in some cases, depending on what type of O&M activities need to be performed. Missing technical documents can be a big barrier as well. In many facilities, especially older ones, it's hard to get documentation related to the facility, either the equipment itself or piping and instrument drawings. Documentation may have been neglected for many years. If you are doing a commissioning type activity, this is an opportunity to start from ground level in putting the documentation together. This includes documentation related to the O&M program, how the facility should operate, the components within the facility, the diagrams, and everything else associated with that facility. That way, you can access those documents in 15 to 20 years to determine whether or not the components and the systems within that building are operating correctly. Commissioning is the time to do this, not later. There's also often inadequate building and equipment metering. Without adequate metering, it's hard to tell whether or not a piece of equipment is operating properly. It's hard to tell if you're saving dollars in steam or fuel unless you have the information at hand to tell you. And this information is generally gleaned from metering. With a lack of management commitment, it's the jobs of the ones involved in O&M to train management on how important O&M is. Another barrier might be poor morale, both from your operations staff, your maintenance staff, and even your management, because the building is in a state of disrepair and things have been breaking for a long time. So how do you sell O&M to management? You have to address the concerns that they have. They may be concerned that the program won't succeed, or they could be concerned that costs are too high and that they don't have the money. They may be concerned that the changes required are too technical. Their confidence level could be affected by their limited understanding of the technologies, or perhaps just of O&M fundamentals. They could also be concerned that they will see no personal benefit or that human resource problems might exist. So you have to understand the decision makers and you have to understand the competition. Who else is fighting for the funding that you want to put towards O&M? You need to speak to the language of the decision makers and have a strong understanding of the project's economics, return on investment, and life cycle costs. Educate yourself to help educate those who make the decisions on the budget. So how long do you get the program off the ground? Well, you should start small and don't bite off more than you can chew. Start with a small piece of equipment that has high opportunity for success, something that has an opportunity to save money from either an energy standpoint or from saving on replacement costs. Keep accurate records. Record the time and cost spent on the project, the maintenance cost savings, and maintenance cost avoidance. These are just a few of the type of things that you want to maintain during this process. If you have adequate metering installed, You can meter fuel costs associated with whichever piece of equipment or system that you've selected. You might be able to record steam flow, temperatures, pressures, or more that can substantiate your efforts. Keeping accurate records can help prove the importance of O&M to management. And then show the data. Share the results to your management. How do you measure the quality of your O&M program? Well, there are various metrics you can use, and here are just a few examples. They're not all-inclusive. Work orders generated and closed out, backlog of corrective maintenance, records of preventive maintenance, your safety records, and energy use. I mentioned that a few seconds ago. You can also look at metrics like your percentage of reactive maintenance versus preventive maintenance, your overtime hours, and dollars, the cost of parts, your replacement costs, and things like this. And now we'll discuss effective operations and maintenance and program management, OMETA. Operations maintenance is not just operations and not just maintenance, but it's comprised of operations, maintenance, engineering support, training, and administration. Each of those entities are just as important as the other. You need to look at your operations and maintenance support and training administration and evaluate their effectiveness and identify any gaps that might exist so that you can improve your process and improve your own end program. Here are a few examples you might want to evaluate within your operation structure. Number 1, organizational structure. Does everyone understand it? Is it well documented? Is the interface of your operations program interfaced with other entities? They could be interfaced with the engineering support, with maintenance, and with administration. Is it understood? Is it documented? And is it well defined? Situations can arise where maintenance on specific components or systems is not performed properly because no one understands the job duty or whose responsibility it is to maintain and/or operate that piece of equipment. Number 2, plant evolution and testing. Are they authorized and controlled? Is someone in charge? Are testing and evolutions looking to ensure that those processes, when they're performed, don't cause a safety concern and they don't cause degradation to your equipment? Use approved procedures. Procedures are very important in operating a plant to ensure that the configuration of the plant is as it should be and that operations are performed in accordance with their best practices and that you're maintaining your equipment or operating your equipment in a manner that the designer intended those components to be operated. And we'll talk more about that when we talk about life cycle. Number 3, operating conditions effectively monitored. This ties into what conditions you're looking at, what parameters you look at, and who looks at those parameters. Operations staff are the ones going out and getting the information from the plant and then logging it. It's very important that you look at various parameters, perhaps across heat exchangers or the oxygen level in the combustion process for a boiler or these types of things. You should define which are parameters important to your system, to your energy consumption, and to the health and welfare of your components. Number 4, maintenance. Is there a work priority system, or do you just react to what's broken on any given day? Do you have work documentation? Do you maintain records related to your machine history and your work activities that you can access downstream to determine what type of maintenance activities are being performed, what are the bulk of maintenance activities, and are these activities reactive or proactive? Number 5, maintenance program implemented. Is the maintenance program implemented, or does maintenance come to work every day trying to figure out what fire they need to put out on that particular day? Number 6, engineering support. The facility may be too small to have a specific engineering department, but if that's the case, they may be able to rely on a larger facility. In any case, engineering support still needs to be part of an O&M program. You need to have sufficient staff and resources, either contracted or within your own facility, to be able to look at design and modification needs, to interface with operations and also maintenance personnel. For the most part, operations and maintenance personnel know where all the problems are in the facility. They've operated it and they've maintained it for quite some time. But occasionally, the engineering department might come in and define a modification or a plant system change without interfacing with the maintenance and operations staff. They could find out very quickly, for example, that their proposed solution is not the one that's going to work. This connection needs to be made. The data collected and trended needs to be reviewed. As well, the information that operations is collecting needs to be defined and used effectively to determine whether or not the facility is operating efficiently or whether there are problems with the equipment. Often, there are facilities where operations do a great job of collecting information. They rigorously log information every 4 hours or more. They change the charts on the recorders and file them, and when a certain time period passes, the records are archived and the process starts over. Rarely does anyone look at the information. It may have been years since anyone thought about what they recorded and why. What does that mean for the energy use or the health and welfare of the equipment? You need to take time to reflect on what you are recording and how it is helping your plant to achieve energy efficiency or extend the life of your equipment. Number 7, configuration control. Again, engineering or technical support expertise is often required to define the matrix of equipment that you need to operate. Number 8, training. Do you have training at your facilities? It's a key element in good O&M. Your operations staff need to be trained for their jobs, otherwise they'll shorten the life of equipment and you won't operate efficiently. Do they understand why certain data points are being logged? Number 9. The same goes for maintenance staff. Maintenance and operations staff want to do a good job but often are not given the tools they need to effectively do their jobs, and they end up operating the building or maintaining the plant in a way that shortens the life of the equipment or throws energy dollars away. You'll need continuing training and some initial training, and one of the key things when you define this training is, does it do what it needs to do? Is it compatible with what the job is, with what the maintenance job is, or with the operations job? And then how do you evaluate whether or not the training you have given is adequate, be it on the job, classroom training, or just reading the manual related to a piece of equipment? You need to have continuous training. Sometimes the engineering department may change a new pump or a new motor or a boiler with the latest technology and then not provide the operations staff and maintenance staff the training they need to be able to do maintenance on that piece of equipment or to operate that piece of equipment. Number 10, administration program. Do you have a program in place to document how to do business, what your O&M program really is? Is work control documented? Is there some place or some entity involved that maintains these records? And configuration control. The job isn't done until the paperwork's done. As discussed earlier, you need to take all the paperwork and organize, track, and maintain those records so that they're accessible in 10 or 20 years. It should be available in case someone in the future wants to look back and ask, how did that boiler operate 10 or 20 years ago when it was first installed? Or how does that compare to where I am today? How much fuel usage do I have today versus 10 years ago, and why? A good O&M program has an integrated structure with strong ties between operations, maintenance, engineering, training, and administration. Operations and maintenance are not just a microcosm unto themselves. If we don't operate like this, our O&M program is not going to be as efficient or as effective as we'd like. Next, we'll be going over the maintenance program. Before getting into the maintenance programs, we're going to go over the component life cycle. What is the component life cycle? It's something we don't think about very often, but it's why we do business, and it's why we operate the way we operate. It's why we maintain components. Here's a very rudimentary life cycle, just a simple diagram to get the point across. At some point in time, there is a new component. The designer intended that that component operate in a specified operational environment with a specific temperature, pressure, clearances, vibration, etc. The component gets installed, and hopefully the design basis is used when the component is operated. Hopefully it's operated within the envelope that the designer intended it to be. The designer recognizes, however, that no component, no system lasts forever. It's going to undergo some level of degradation. If the component is maintained correctly, it will maintain the rate of degradation that the designer intended. There are some other things that have to be done to maintain that degradation rate. We have to perform various maintenance activities that the designer intended to be performed on that component. Similar to the design of your car, which intended you to change the oil every so often, the designer of most components intends you to perform some level of preventive maintenance on a regular basis. There's also repair refurbishment. Wheel bearings don't last forever, fan belts don't last forever, so we have to refurbish or repair various parts of most components we talk about to maintain that component and get the design life out of the component. At some point in time, at the end of the design life, it will no longer be cost-effective to refurbish the component. It's worn out, and at that point in time, the component is replaced and the cycle starts all over. But what happens when things go wrong if we don't operate or maintain that component? Well, we'll shorten its life. We could use a component in an incorrect application and induce stressors in that component that wouldn't normally exist. We could operate that component in an off-normal operation, outside the envelope that the designer originally intended. We could perform maintenance on that component, there could be improper maintenance, or we just don't do the maintenance that's required. All these things can add up and change the rate of degradation that that component experiences and leads to premature failure. Now we're going to talk about maintenance programs and practices. What are maintenance programs and what are maintenance practices? Well, basically maintenance is trying to minimize the degradation of a piece of equipment and extend its life to design to what the designer intended. There are various maintenance program options. There's reactive maintenance, preventive maintenance, predictive maintenance, and reliability-centered maintenance. And we'll talk about each of these in a little bit more detail. Reactive maintenance is the predominant method of maintenance, but does very little to get the life out of a component that the designer intended. Reactive maintenance basically just says, run it until it breaks. It's been the typical mode of maintenance for not only the federal sector but also the private sector for quite some time. Reactive maintenance advantages. This should really be perceived advantages. If nothing's breaking and there aren't any major issues at the facility, reactive maintenance should be perceived as an advantage since it costs less both in terms of staff and capital costs. In reality, it's the opposite. Reactive maintenance programs lead to unplanned downtime. You're not going to have a reliable building. You could also see increased labor costs if something breaks down outside of regular work hours. Repair and replacement costs. There are obvious costs associated with the component in replacing or repairing it. Also, there are going to be costs associated with trying to maintain parts inventory on stock to keep all the components working. With secondary equipment damage, when something breaks, it often causes something else to break. As an example, cars generally have some type of timing belt or timing gear. In many cars, this only costs a few $100s to replace and should be done, say, every 100,000 to 150,000 kilometers depending on the car manufacturer's recommendations. But if we wait, in some cases, this belt can fail and cause secondary damage of the engine, and which may cost many thousands of dollars. It's a case of the primary component, the belt or chain. A breakage causes secondary damage and inefficient use of staff resources. Reactive maintenance is just inefficient. The next maintenance option we have is preventive maintenance. What are we trying to do with any preventive maintenance program other than reactive maintenance is to extend the life of a component to its design life while trying to maintain energy efficiency and optimum operation of our plant. Preventive maintenance type tasks that we talked about in the design or life cycle design are things like changing oil and replacing filters and greasing bearings, these types of things. And these tasks are done periodically. Their maintenance period can be marked by calendar days, runtime, or parts produced. These maintenance activities are not performed based on the actual condition of the machine. They're performed through recommendations and engineering experience. These maintenance activities are useful against degradation-type modes of wear, fatigue, and corrosion, and you might think of it as analogous to the automobile schedule of maintenance. We all know that when we purchase our new car and it's warrantied for 50,000 to 100,000 kilometers, that the warranty is contingent on performing preventive maintenance. When you open the manual, it will have a maintenance schedule that says, for every 5,000 kilometers, do this, or 10,000 kilometers, do this. The car manufacturer is confident that if you perform the preventive maintenance tasks and operate the car correctly, the warranty is going to last and you'll get the design life out of the vehicle. It's the same way at our facilities. If preventive maintenance is performed correctly, it extends the life of the components and the system and saves money due to energy consumption. What are the advantages of preventive maintenance? We've already touched on a few. It's cost-effective, it can extend the life of our components, it saves energy, it increases the component life cycle, and it increases the reliability of the plant. Also, preventive maintenance is flexible. It's flexible in that you might schedule the task for one time frame, but still have flexibility to move it. If I change oil every 5,000 kilometers in one case, I might change it every 4,800 kilometers in another case, or I might wait until 5,500 kilometers before I change the oil. It does have flexibility. There are some disadvantages though, especially compared to predictive maintenance. You're still likely to have failures. Preventive maintenance won't take care of and mitigate all the failures you might experience within a plant or a plant's equipment. It's labor intensive, and if things aren't breaking, you probably don't need someone to go around and do preventive maintenance in the near term. But in the longer term, it does pay off. Another disadvantage is the performance of unneeded maintenance. In some cases, if maintenance is being done based on a schedule and not based on the actual condition or the machine, we can perform unneeded maintenance. We might change a belt on a fan that doesn't need changing, or change oil in a large oil reservoir that doesn't need to be changed. It may just be fine chemically. There can't be incidental damage to components through poor maintenance practices. Many of us have seen the bathtub curve related to the probability of an equipment failure shortly after a major maintenance overhaul. We can, in fact, through preventive maintenance, actually cause damage to our components. This is where some of other key entities and key elements that I spoke of earlier in OMETA can assist and are very important. Do we have adequate documentation to support the maintenance staff during this overhaul or during this maintenance activity? Do they have the proper manufacturer's guidelines? Are they properly trained? And do they know what to do and how to do it? So how do you build a preventive maintenance program? Well, first of all, you need a master equipment list. This list is important whether you're talking preventive maintenance, predictive maintenance, or reliability-centered maintenance. You have to know what's under your umbrella, and a key time to do that is at building commissioning stage. This is when you'll have everyone involved in building operations together, and you'll have all the documentation on hand. Put all the documentation together and make sure that it's collected and stored and filed so you can access it in, say, 30 years. You should also have drawings of the facility and know how it should be operated. Assign components into logical groups and prioritize components based on importance to the process. We'll talk more about some prioritization of equipment importance when we get to reliability-centered maintenance, but it's still important in a preventive maintenance program. You need to look at the components with respect to their importance to the process and their importance to energy efficiency. Then you have to determine the type of maintenance staff required to perform most maintenance tasks on the equipment. You'll also have to determine how frequently the maintenance tasks are going to be performed. Will it be daily, weekly, quarterly, or annually? Maybe every 6 weeks. Maybe every 6 years. You can use technical manuals, machine history, your engineering department, good engineering judgment, or root cause analysis to make this decision. If you have the foresight to maintain good equipment history and machine history, you can look at the failures in the past and hopefully figure out why it failed and take actions to change how you do business, how your maintenance is performed, so you can decrease the failure rate of that specific equipment or component. Prepare a schedule of maintenance activities to perform during outages, recognizing that outages and the tasks during outages fall outside of the daily, weekly, monthly type activities. If possible, incorporate a schedule in a computer-based management system. It's more accurate and it eases the report generating process, and it's also easy to update your system. Some studies have shown that such a system can increase the maintenance productivity and can decrease the equipment downtime while decreasing the parts inventory. And it also saves on material costs. Provide a method to monitor your program maintenance using the metrics talked about earlier as far as downtime and how much reactive maintenance you're doing versus preventive maintenance, the reliability at your facility, its energy use, etc. Predictive maintenance is different than preventive maintenance since it assesses the condition of the machinery or the components through measurements. It doesn't rely on a schedule. It asks the questions, what type of condition is this machine in? Are there stresses that exist within this component that are degrading this machine at a rate greater than design? Am I operating this machine in such a way that I'm shortening its life? If I am, then I want to take the action necessary to mitigate the stresses. In a predictive maintenance program, you would measure the component stress levels before they can cause a problem. You can measure component stresses through vibration, thermography, and oil analysis. You can measure the degradation mechanism and evaluate component performance through its power consumption. Are there advantages to predictive maintenance over preventive maintenance? Yes, very much so. It can increase component operational life and availability. We're no longer guessing if stresses exist and taking maintenance actions. We're actually measuring whether they do or not. Because of that, it provides us the flexibility to say when and how we need to do maintenance. What tasks do we need to do? And we can schedule these tasks. Since you know the condition of the machine, you can plan when you do the maintenance task accordingly. This makes it easier to schedule maintenance hours. You can schedule it during the day, and you don't have to schedule overtime hours and associated costs. At the same time, you can order your parts. You know when you're going to do maintenance, so you no longer need to maintain that inventory, that stockpile of parts, and you can let your distributor maintain that themselves. This results in significant cost savings in many cases. And if things are operating optimally, if your plant is operating at a high degree of reliability and things aren't breaking, you have a safe environment and your worker morale improves as well. There are also energy savings. If the plant is operating as it should be, the components are running efficiently and effectively, you won't have steam leaks, you won't be blowing through the steam traps, and the boilers will operate at a higher thermal efficiency because you've taken care of issues like scaling. Are there disadvantages? Yes, of course. Predictive maintenance technologies are expensive. Diagnostic equipment can cost thousands of dollars. One could easily spend tens of thousands of dollars on an infrared camera, for example. There's also increased investment and training of staff. Predictive maintenance technologies are not only costly, they're not intuitive. They require some training to be able to use. Different technologies require different levels of training, but none of them are off the shelf. They all require some level of training, and there's a cost associated with that. Often, the saving potentials are not readily seen by management. It's a hard sell to go to management and say, I want to buy an infrared camera for $60,000. It probably won't be in the budget unless you can substantiate that with some payback and some return on investment, it's viable. In some cases, you can, depending on the type of facility you have and the type of maintenance that you perform with that infrared camera or predictive maintenance. In many cases, though, you can't. And in those cases, you may be able to contract the services instead. That $60,000 infrared camera just turned into a periodic inspection by contract services for $1,200 to $1,500 a day, maybe once or twice a year. So you can glean a report and the information necessary to define the health of the equipment of your systems and use that to generate your needed maintenance activities downstream and prioritize them. With reliability-centered maintenance, we can take predictive maintenance a step further. We recognize that predictive maintenance is costly as far as equipment and resources, training, and people are concerned. We also realize that reactive maintenance across the board is not a good way to do business. We understand that some equipment is critical to our mission and critical to, say, energy efficiency or, in many cases, safety. Once we understand and recognize this, reliability-centered maintenance then says, let's mold our O&M program around these differences and let's do reactive maintenance where it makes sense. You'll have to prioritize your equipment based on its importance. Reliability-centered maintenance looks at the type of failures that are likely to occur within your key components or with mission-important components as you define them. These components generally have some type of failure rate associated with them just because of the nature of their function and how often they are used. The failures will have some type of effect upon your mission and upon what you deem as important. So what reliability-centered maintenance does is try to aim resources at predicting the failures that have the greatest impact to your mission or system. This includes aspects of reactive preventive maintenance concepts. With some equipment, you may just perform preventive maintenance. With other equipment, you'll perform a combination of preventive and predictive maintenance. Reliability-centered maintenance was pioneered by industries that need to be reliable, otherwise people's lives are lost. For example, nuclear power plants, airline industries, and fossil fuel power plants. These are the type of industries that need a high degree of reliability, but still have limited resources. So they need to define which equipment and which systems are important to maintain to keep the highest degree of reliability. And they do that with a reliability-centered concept. There are 3 tasks for reliability-centered maintenance. First, you define what's important, you define what type of failure modes exist, and the effect of those failure modes on your process. Then identify effective maintenance tasks or mitigation strategies. Based on that, you determine what maintenance activities you can perform so that those failures don't occur. Then you would integrate that into your existing maintenance program. There are many of the same advantages that we see with predictive maintenance technologies. There's increased reliability, reduced chance of sudden equipment failure, and lower costs by eliminating unnecessary maintenance or overhauls. You're also able to focus maintenance activities on critical components, increase component reliability, and incorporate root cause analysis. Are there disadvantages? Yes. The disadvantages include workforce, equipment, and training. Many of the same disadvantages we see in predictive maintenance technologies because reliability-centered maintenance is so predictive maintenance technology heavy. The reliability-centered maintenance is a premier program, and you can integrate its principles and backfit your own maintenance program. However, it will take some time and effort. So why change? It could be cost savings. This example shows that a plant with 100 steam traps and a 20% failure rate can easily lead to costs of over $150,000 per year. It could be something else. It could be maintaining continuity of R&D efforts or plant safety. You can't have 50% reactive maintenance and have a safe and reliable system. Reactive maintenance requires extra inventory, and it costs downtime, energy, overtime, and unplanned equipment failure. The bottom line is reactive maintenance is not the way to go. So in conclusion, to have successful operations and maintenance, you want to follow these principles. Start your program development early. Recognize program entities, OMITA. Operations is not just operations, and maintenance is not just maintenance. Operations, maintenance, engineering, training, and administration have to be all equal parts of your O&M program. Evaluate your needs. For some equipment, reactive maintenance is fine. For some equipment, you'll have to go to predictive to maintain its optimum reliability. And document your program results. Documentation is key to maintaining your system and maintaining your O&M program. Here are a few resources to get you started. We've provided the U.S. Department of Energy's O&M Best Practices Guide, as well as NRCan's guides to commissioning, recommissioning, and ongoing commissioning. Now we will go over 10 quiz questions to test what we've learned. Question 1. Which of the following defines operating and maintaining a component as the designer intended? A. Preventive maintenance. B. Predictive maintenance. C. Reliability maintenance. D. Design basis operation. Or E. Schedule maintenance. The answer to the first question is A. Preventive maintenance. Question 2. Which of the following defines actions that detect, preclude, or mitigate degradation of a component or system with the aim of sustaining or extending its useful life by controlling degradation to an acceptable level? A. Reactive maintenance. B. Design basis operation. C. Design basis degradation. D. Preventive maintenance. Or E. Predictive maintenance. The answer to question 2 is D. Preventive maintenance. Question 3. Which of the following shows the equation for determining risk priority numbers in reliability-centered maintenance? A. Criticality times failure rate times detection probability. B. Severity times failure rate times detection probability. C. Severity times failure rate times criticality. D. Failure rate times severity times detection probability. Or E. Effect times failure rate times severity. The answer to question 3 is B. Severity times failure rate times detection probability. Question 4. Which of the following is not a major integrated function within the OMITA acronym? A. Administration. B. Engineering support. C. Energy efficiency. D. Training. Or E. Maintenance. The answer to question 4 is C. Energy efficiency. Question 5. Which of the following maintenance practices is considered the premier or ideal approach to maintenance practices? A. Reliability-centered. B. Predictive. C. Preventive. D. Reactive. Or E. None of the above. The answer to question 5 is B. Predictive. Question 6. Which of the following describes a systematic process for assuring by verification and documentation from the design phase to the post-construction phase that all facilities perform interactively in accordance with the design documentation intent and operational needs? A. Preventive maintenance. B. Commissioning. C. Diagnostic monitoring. D. Equipment efficiency. Or E. Operations and Maintenance Assessment. The answer to question 6 is B, commissioning. Question 7. Which of the following are factors used in establishing a baseline for O&M projects? A, energy consumption values, B, failure rates, C, production downtime, D, all of the above, or E, none of the above. The answer to question 7 is D, all of the above. Question 8. Which of the following is not recommended when selecting early projects in O&M? A, select an entire system to address root cause. B, select troubled equipment. C, elect situations that will provide immediate positive results. D, start small. Or E, keep accurate records of time and costs. The answer to question 8 is A, select an entire system to address root cause. Question 9. Which of the following best describes the practice of collecting equipment operation data over a period of time to assess performance? A, an energy management system. B, a data logger. C, diagnostic monitoring. D, predictive maintenance. Or E, reactive maintenance. The answer to question 9 is C, diagnostic monitoring. Question 10. Which of the following is the ideal commissioning type for older facilities that have never been through the commissioning process? A, commissioning. B, recommissioning. C, retro-commissioning. D, continuous commissioning. Or E, none of the above. The answer to question 10 is C, retro-commissioning. Here's our contact information if you have any questions concerning the course material. Thank you for participating.